Hello, good evening. My name is Parth Joshi. So I am a PhD student in the Department of Mechanical Engineering at IIT Bombay. So I'll be conducting the tutorial sessions for this week. So I have been conducting weekly tutorial sessions since the last 4 weeks. So till now we have covered the concepts related to free vibration and forced vibration, and in the last week we discussed about equivalent damping. So in this week we would be discussing the problems related to the vibration measuring instruments. So, so I would like to, before we begin, I would like to thank the CMRF team and the NPTEL team for giving me this opportunity to conduct these weekly tutorial sessions. So the topics that have been covered for this, the week content for this week are transducers and vibration pickups. So transducers are the uh, kind of substances or like devices where which convert mechanical forces or like pressure into equivalent electrical signals. So they convert, transform once the desired mechanical vibrations or like forces and stresses into equivalent electrical signals. And vibration pickups are basically transducers which are being used in a certain way so as to measure the vibration signals. A vibrometer is like another concept which has been covered for this week. So vibrometer, or they are also called a seismometer. So they basically measure the displacement of any vibrating structure. So if we attach this vibrometer to a certain vibrating structure, it will provide a signal which is proportional to the displacement. And the next thing is about accelerometers, so which are very popularly used in dynamics related experiments. So, so these are devices in which uh, we uh, we are able to measure the acceleration of the vibrating structure. So it provides us a voltage which signal which is proportional to the acceleration of the vibrating structure. The next concept is about velocity pickup or velometer. So which again similarly gives us an electrical signal which is proportional to the velocity of a vibrating structure. So all of these vibration instruments, they can be modeled as uh, like a spring mass damper system. So let us say if our vibrating structure is uh, like oscillating uh, at a rate given by y of t, so which is represented by the hatched uh, lines over here. So this is the vibrating structure, and to that we have attached this vibration pickup. So which is basically, this can be modeled as a spring mass damper system. So the suspended mass m, small m, represents basically the pickup, the seismic mass or pickup mass, whatever. And let us say it is moving at uh, a certain rate, and its displacement with respect to time is given by x of t. So it is attached to this vibrating structure through a spring of stiffness K, and and also through a damper which has a damping constant of C. And T here, T is over here, is represents like the transducer over here. So let us say if the displacement of the vibrating structure y of t is given by y sine omega t. So we define a relative displacement over here, which is called as z over here. So which is the difference between x and y. So x minus y. So that is the relative displacement that is actually being measured over here. So if we write down the, if we actually draw the free body diagram of this mass and show the forces, and then write the differential equation, and by applying the Newton's second law to this system, we get the differential equation of this form: mz double dot plus cz dot plus kz is equal to minus my double dot. So this expression is similar to the left hand side represents uh, the differential equation in terms of z, and the right hand side is similar to having a forced vibrations with this forcing, with a harmonic forcing. So if we substitute a solution of the form z of t is equal to z sine omega t minus phi, so we can solve for the steady state amplitude z in terms of the steady state amplitude y of the vibrating structure, and the variation of these, the ratio of the steady state amplitude z and y, we can obtain it with respect to the frequency. So we can solve for this steady state amplitude z as a function of the steady state amplitude y and the frequency, the mass, stiffness, and damping properties. So we can graphically represent this the ratio z by y with respect to the frequency ratio omega by omega n. So we can see that when uh, as the frequency goes on increasing, the steady state amplitude goes on increasing, and when it is when this frequency ratio matches the natural frequency, so there we say that the steady state amplitude actually goes on increasing, and then as the uh, frequency ratio increases, this amplitude ratio converges to nearly 1. So for the frequency ratio greater than 3, we can see that this ratio z by y is nearly equal to 1. So that is called as the range for vibrometer. So what we would expect, like if to for the measurement by the vibrometer to be accurate, we would expect that the quantity z, which is basically the relative displacement between the seismic mass and the vibrating structure. So let us say x minus y should be actually nearly equal to y itself. So the so when the frequency uh, of the of vibration divided by the natural frequency, when that is very high, so then we can expect that the quantity x to be nearly 0, or z is very close to y. So z by y becomes nearly equal to 1 for this range of frequency ratios. Whereas in case of accelerometers, it is the opposite. So accelerometers generally tend to have very high natural frequency. So the range in which they operate, they typically represent the range where the frequency ratio is actually significantly less than 1. So, uh, so in case of vibrometers, we can like expect, we can visualize it in terms of a system which has a low natural frequency, so which means that it has a lower stiffness and very high mass. So the seismic mass must be significantly large for this vibrometers or seismometer kind of instruments. So so that's how we get the range for the vibrometer. So this was an overview of the concept. So and largely we can derive the similar equations for the accelerometer and as well as the velometer uh, by following a similar approach. So let us proceed to some of the example problems. So let us start with some of the example problems which are related to this concept of vibration measuring instruments. So in the first question, it is asked which of the following instruments measure the amplitude of the vibrating body. So as we just saw, uh, the vibrometers and seismometers are the instruments that measure the amplitude of a vibrating body. So, so the correct answer to this question is both A and B. So the next question is which of the following statements is true about stroboscope? So stroboscope is a frequency measurement instrument. So generally it is used uh, for measuring the RPM of let us say some rotating bodies. So if we want to measure the speed of rotation of a shaft without with using a like a non-contact method, then stroboscope is one of the useful methods for that. So in a stroboscope, what happens is that a light is emitted at a certain frequency, and what happens is that if we put some characteristic markers on the rotating surface. Let us say if we have a certain cylinder and we have a certain kind of a pattern or markers on which we shine light on the surface. So when the light is shined on the surface using a stroboscope at a certain frequency, and as we go on varying the frequency with which the light the of the stroboscope, so when it matches the frequency of rotation of the actual rotating part, so then the pattern which appears on the surface, it appears to be stationary. So at that point, the frequency of the stroboscope matches the frequency of rotation of whatever that rotating shaft, etc. So that's how we can use this technique to measure the frequency or speed of rotation. So the correct answer to this question is stroboscope is a non-contact type frequency measuring instrument. So the next question is asked like about uh, a device that transforms the values of physical variables into equivalent electrical signals. So such a device which performs transforms the value of physical variables into electrical signals. So we discussed that these are called as transducers. So for example, we have strain gauges. So strain gauge is an example where uh, the resistance of the strain gauges changes with the deformation. The other example is of piezoelectric materials, where depending on the pressure that is applied to between opposite surfaces, the there are opposite charges like positive and negative charges which get accumulated over the other two ends, so that causes generate some voltage. So basically pressure or force is converted into an equivalent electrical voltage. So likewise, there are many examples also like apart from that, which is called LVDT or uh, linearly varying differential transformer or transducer. So that is also another example. So then we also have a capacitive transducer. So where the capacitance of the surface, like let us say if we have a parallel plate capacitor, its capacitance is given by epsilon A by D. So if let us say if we change the surface area or the spacing d between the parallel plates of the capacitor, so then it will produce a proportionate change in the capacitance, and then subsequently it will produce a change in the voltage which is observed across the capacitor terminals. So that can also be considered as a example of a transducer. Yeah. So the next question is, for proper vibration isolation in a forced excitation system, the spring should be selected so that which of these following conditions are satisfied. So, so for forced vibrations, uh, we saw that the ratio Z by Y, it was given by R square upon a square root of 1 minus R square the whole square plus 2 zeta R whole square. So if we plot this ratio Z by Y with respect to R, so when R is equal to 0, this ratio Z by Y is equal to 0. And so uh, as we go on increasing the frequency ratio, this ratio of Z by Y asymptotically approaches the value of 1 for higher values of frequency ratio. So when the frequency ratio is generally when it is greater than or equal to 3, then that results in effective vibration isolation. Uh, so in effective convergence as well as vibration isolation. So let us look at the next question. A vibrometer shows 5% error in measurement and its natural frequency is 4 Hz. So if the lowest frequency that it can measure is 8 Hz, then the value of the damping ratio zeta will be what? So, so as we saw that for a vibrometer, this amplitude ratio Z by Y is given by R square upon square root of 1 minus R square the whole square plus 2 zeta R the whole square. Now it is given that the vibrometer shows 5% error in measurement and its natural frequency is given to be omega n is 4 Hertz. So if so let us say it is operating at a frequency of 8 Hertz, which is given as the lowest frequency that it can measure. So then R is equal to omega by omega n, which is equal to 2. So it is given that the vibrometer shows 5% error in the measurement. So when we say Z by Y, so Z is actually the measured signal and the Y is the actual one. So, so when we say that there is a 5% error in measurement, so it means that z minus y upon y is actually equal to 5% or 5 by 100. So therefore z by y is equal to 1.05. So using this z by y is equal to 1.05 and r is equal to 2. So we can get an equation of z by y is 1.05 is equal to 2 square upon square root of 1 minus 2 square to the whole square plus 2 into theta into 2 the whole square. So using this the given data we get the equation in terms of the damping ratio. So we can solve this equation to get the value of damping. So 1.05 is basically given by 4 on square root of 1 minus 4 the whole square or 3 square plus 2 into zeta into 2 whole square. So we get 4 upon 1.05 the whole square is equal to 9 plus 4 into 4 the whole square is 16 zeta square. So therefore we can write zeta square is equal to 4 upon 1.05 the whole square minus 9 divided by 16. So theta will be square root of 16 by 1.05 square minus 9 divided by 16, the whole thing under the root. So we can solve this equation to find out the value of zeta. So it is equal to 16 divided by 1.05 whole square. So this quantity minus 9. So this quantity divided by 16 and finally zeta is basically square root of this quantity which is 0.586. So the correct option is C, 0.586. So let us move on to the next question. A vibration measuring device is used to find the acceleration of a machine running at 200 rpm. So it is given that the natural frequency of the instrument is 10 Hz and it is showing a displacement of 0.008 centimeter. So then what will be the acceleration reading? So we again go back to our original equation for any vibration measuring instrument, which is z by y is equal to r square upon square root of 1 minus r square the whole square plus 2 zeta r whole square. Now here we have not been provided with any information related to damping. So let us assume that damping is nearly 0. So it is also given that omega n is 10 Hertz and the machine is running at 200 RPM. So how do we calculate omega from that? So omega is 2 pi n by 60, which is 2 pi into 200 by 60. So which is equal to 20 pi by 3 into in hertz. It's in actually radian per second. So this omega in hertz will be uh, 20 pi by 3 into 1 upon 2 pi. So because frequency is omega by 2 pi, so which is 10 pi 3 hertz. So the frequency ratio R, which is equal to omega by omega n, is 10 by 3 upon 10, which is equal to 1 by 3. And we have also assumed that zeta is equal to 0. So it is given that it shows a displacement of 0.008 centimeter. So Z is the displacement that it actually is measuring. So let us say that Z is equal to 0.008 centimeter. So using this information, let us try to find out what is the ratio of Z by Y is equal to R square upon 1 minus R square square root of so it is equal to R square upon mod of 1 minus R square, which is 1 by 3 whole square upon 1 minus 1 by 3 whole square. 1 by 9 upon 1 minus 1 by 9, which is 1 upon 8. So Z is also, we have been given that it is 0.08008 centimeter divided by is 1 upon 8. So Y is equal to 8 into 0.008 centimeter. So the acceleration, it can be given as omega square y as the amplitude. So here omega, we have found out that it is 20 pi by 3 radians per second. So that will give us the angular frequency in terms of radian per second 20 pi by 3 into 0.064. So so 20 pi by 3 whole square. So this quantity into 0.064, which gives us 28.07 as the answer. So let us look at the options. So our option closely matches the option A, 28.08. So that is our acceleration reading. So the correct answer can be option A. So let us look at our next problem. An accelerometer has a suspended mass of 0.01 kg mounted on an engine which is undergoing an acceleration of 9.81 meter per second square at an operating speed of the engine, which is 5000 rpm, and it records the acceleration as 10 meter per second square. So if the damping ratio is 0, then the spring stiffness of the acceleration is something that we need to find out. So if we draw the diagram of this system, so let us say there is a small accelerometer which is mounted on the surface of the engine, which has a small mass m. We have been given that there is no damping, so we can just consider the stiffness only. So it has been given that mass m is equal to 0.01 kg. So let us say this engine is undergoing some acceleration. So the acceleration of the engine is y double dot, so which is 9.81 meter per second square. So it is given that this engine is operating at a speed of 5000 rpm. So omega is 5000 into 2 pi by 60. So which is equal to 500 pi by 3 radians per second. So this is the omega. So it is given that it records an acceleration of 10 meter per second square. So we can write down that as uh, so the true value of acceleration measured by y. So z upon r square y. So for an accelerometer, uh, the ratio, that is the ratio that we consider, is equal to 1 upon square root of 1 minus r square the whole square plus 2 zeta r whole square. So it is given that damping zeta is equal to 0, which is therefore equal to 1 upon 1 minus r square. So this has been given as 10 upon 9.81. So therefore 1 minus r square is equal to 9.81 by 10, or r square is equal to 1 minus 0.981, or r is equal to square root of 1 minus 0.981. So therefore r is equal to 0.1378. So we got the value of r. So the value of r is basically omega by omega n, and we already know omega is equal to 500 pi by 3. So omega n will be omega by r, which is 500 pi by 3 upon r, which is 0.1378. So we find out that omega n is equal to 500 into pi by 3 divided by r, so which is equal to 3798.6 radians per second. So we already know that the natural frequency omega n is root k by m, and it is given that the accelerometer has a suspended mass of 0.01 kg. So we already know m. So therefore k is equal to 3798.6 whole square into 0.01. The value of k is nearly 144.3 kilonewtons per meter. So if you look at the options, so the option C seems to be the closest one. So that is the correct answer. 1.144.3. An accelerometer, the next question is, an accelerometer has a damping ratio of 0.8 and the value of the frequency ratio is 2. So we have to find out the ratio of steady state relative displacement to the amplitude of input displacement. So it is given that zeta is equal to 0.8 and the value of frequency ratio R is equal to 2. So we again go back to our original equation of ratio of the steady state relative displacement to the amplitude of input displacement, which is so Z is basically the steady state relative displacement, whereas Y represents the amplitude of input displacement or amplitude of vibrations of the actual vibrating surface. So the ratio of Z by Y is given by R square upon square root of 1 minus R square the whole square plus 2 zeta R whole square. So it is already given that R is equal to 2. So R square is equal to 4. The square root of 1 minus R square is equal to 1 minus 4 the whole square plus 2 into 0.8, so which is value of zeta into 2. So this value of the ratio of amplitude Z by Y, it works out to be 4 upon square root of 9 plus 16 into 0.64, which is can be calculated 4 upon square root of 9 plus 16 into 0.64, so which nearly works out to be 0.91. So the correct answer to this question is option B, 0.91. So let us move on to our next question. A seismic instrument has a natural frequency of 2 Hz and a damping ratio of 0.6. So it is given that omega n is 2 Hz and the omega, which is the frequency of excitation, is 3 Hz. The damping ratio zeta is 0.6. So then it has been asked what is the error due to the proximity of the exciting frequency with the natural frequency of the instrument. So if we look at the plot of the amplitude ratio z by y, so which is given by this our usual equation of r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. So if you look at the plot of this equation, so the amplitude ratio of z by y with respect to r, so then this plot initially increases, and so in the vicinity of r is equal to 1, when it matches the natural frequency, the amplitude ratio is very high, and as we go to higher and higher values of frequency ratio, this amplitude ratio asymptotically converges to. So the plot of the amplitude ratio z by y, it asymptotically converges to 1 for very high values of frequency ratio. So, so when we are operating at a certain frequency, so then this is uh, the z by y ratio which is measured. So it will be somewhat greater than 1 over here. So then z is basically represents the measured quantity and y represents the actual one. So the error would be basically z minus y by y. So that is something that we need to find out. So based on the given information, let us find out the amplitude ratio z by y. So z by y is given by r square upon square root of 1 minus r square the whole square plus 2 zeta r whole square. Now here r is basically omega by omega n, and it is being given that omega is 3 Hz and omega n is 2 Hz. So r is actually 1.5. So therefore, and zeta is already given to be 0.6. So z by y comes root of 1.5 square to 1 minus 1.5 square the whole square plus 2 into 0.6 into 1.5 whole square. So we can calculate this in again in Excel. So here our value of R is 1.5 and our zeta is 0.6. So numerator is basically R square and the denominator is equal to the square root of 1 minus R square the whole square plus 2 into zeta into R the whole square. So the ratio of numerator to the denominator is 1.026. So therefore the error, which is z by y, z minus y divided by y, which is z by y minus 1, which is 0.0267. So in terms of percentage, it is basically equal to 0.0267 into 100, which is 2.67%. So the correct answer to this question is option D. So let us move on to our next question. So it is given that a spring mass system with mass is equal to 0.8 kg and K is 10,000 Newton per meter. So it is used as a vibration pickup. So let us draw a diagram of this system. So the structure is vibrating with y of t, and let us say the mass is vibrating at x of t. So the relative displacement is x minus y. So let us say y t is y sine omega t. So it is also given that the total displacement of the mass of the pickup x of t. So this is the pickup mass. So that is given to be, let us say, some x sine omega t minus phi. So it has been given that capital X is 10 mm, whereas Y has an amplitude of 5 mm. So therefore Z is equal to X minus Y, which is 10 minus 5, which is again 5 mm. Therefore, z by y will be 5 by 5, which is equal to 1. So we can equate this to the equation for the vibration measuring instrument, which is equal to r square upon root of 1 minus r square to r whole square into 2 zeta r whole square. So here it has been given that the damping is negligible. So therefore this term would be 0. So it is equal to r square upon mod of 1 minus r square the whole square. So r, because of the square root, becomes mod of 1 minus r square. So we have two possibilities. So r square upon 1 minus r square will be equal to plus or minus 1. So r square, so 1 minus r, so r square is equal to 1 minus r square gives us 2r square is equal to 1, or r is equal to 1 by root square root of 2, which is nearly equal to 0.707. And the other possibility is r square upon 1 minus r square is equal to minus 1. So So it gives us r square is equal to minus 1 plus r square. So this has really no solution. So, so therefore this is not possible. So our correct solution is r is equal to 0.707. Since we already know what is the stiffness and damping, so stiffness has been given as 10,000 newtons per meter. And the mass is given as 0.8 kg. So we can find out what is the natural frequency omega n is root of k by m, which is square root of 10,000 by 0.8, which is something around 111.8 radians per second. So omega will be omega by omega n is given to be 1 by root 2. So in terms of radians per second, the answer is omega is 79.06 radians per second. So in terms of hertz, so it is 79.06 divided by 2 pi is equal to is 12.58 hertz. So the correct answer to this question is 12.58, which is option A. So let us proceed to our next question. It is given that a 5 kg mass is suspended in a box by a spring, as it is shown in the figure. The box is put on a platform having a vibration with amplitude y is equal to sine of 8t. So the amplitude of vibration of this platform is y of t, which is sine 8 of t, 8t. So K is given to be 8000 Newton per meter, and the mass is given to be 5 kg. So because this box is rigidly attached to the structure, so we can say that the vibration of the topmost point of the spring is also y of t, and let us call the displacement of the mass as x of t. So let us draw the free body diagram for this system. So let us say the mass is moving upwards, then the spring force will be, let us say, compressive, or like if, let us say, if y happens to be greater than x, so then we can write the spring force as k into y minus x. So therefore mx double dot. So if we apply Newton's second law to this mass, small m, so we can write down the forces as k into y minus x. So therefore we can rearrange the terms. Say mx double dot plus k is equal to y. So let us now substitute the relative displacement as x minus y. So therefore we can write x is equal to z plus y. So therefore x double dot will be can be written as z double dot plus y double dot. So therefore I can write it as m into z double dot plus y double dot plus k into z plus y is equal to ky. So therefore mz double dot plus my double dot plus kz plus ky is equal to ky. So the term ky gets cancelled. Therefore we get the equation as mz double dot plus kz is equal to minus my double dot. So this represents the post oscillation because of my double dot. So if we let us say if we substitute a solution for z, let us say z is equal to z of t, let us say is equal to capital Z e raised to j omega t, and for y of t is capital Y e to the power j omega t, where z and y can be any complex numbers. And let us substitute these two solutions in this differential equation. So z double dot will become, or rather z dot will be j omega z e to the power j omega t, and z double dot will be equal to j omega whole square z e to the power j omega t, or minus omega square z e to the power j omega t. And similarly y double dot will be minus omega square y e to the power j omega t. So if we substitute this into the differential equation, mz double dot plus kz is equal to minus my double dot. So we can write it as m into, so minus omega square z e to the power j omega t plus k z e to the power j omega t is equal to m minus of m minus omega square y e to the power j omega t. So therefore we can write k minus m omega square z is equal to m omega square y. or in other words we can write z by y is equal to m omega square upon k minus m omega square. So it has been given that y is a sinusoidal displacement of sine of 8t, which gives us the information that omega is equal to 8. And K has been given as 8000 and mass is 5 kg. So if we substitute this, we get z by y is 5 into 8 square upon 8000 minus 5 into 8 square. 64 into 5 upon 8000 minus 64 into 12. So 64 into 5 is basically 20. Z by y is basically 320 upon 8000 minus 320. Which is equal to 1 upon 25 minus 1, which is 1 upon 24. Which is given by 0.041667. So the correct option is and C 0.0417. Because Z by Y is 0.0417 and Y is equal to 1 is already given. So therefore Z by Y is 0.0417, nearly equal to 0.0417 centimeter. So here, if we carefully look at our graph, so here omega n will be root of k by m, which is root of 8000 by mass m is given as 5 kg. 1600 is 40 radians per second, and it is given that omega is equal to 8. Omega is given as 8, so therefore omega by omega n is 8 by 40, which is 1 upon 5, which is equal to 0.2. So therefore R, or the frequency ratio, is 0.2, which is significantly less than 1. So we can see that it is operating somewhere in this range between 0 to 1. So this is the range for the accelerometer. So here Z by Y is equal to less than 1 for R is where R is much less than 1. So as we could see that Z by Y is equal to 0.0417, so which is actually significantly less than 1. So yeah, we can observe that this follows this trend and is in the range which is prescribed for the accelerometers. So let us now look at another problem. So it is given that a vibrometer has a natural frequency of 4 radians per second and zeta is equal to 0.1. Omega n is 4 radians per second and zeta is equal to 0.1. So if the difference between the maximum and minimum recorded values is 8 mm, so if when omega is 50 radians per second, we have to find out what is the amplitude of the vibrating structure. So the difference between the maximum and minimum recorded values, so basically the amplitude of Z is 8 by 2. So let us say if Z is the recorded value, so the difference between the max and minimum values will be twice the amplitude of the Z. So let us say if Z has some sinusoidal nature, so the difference between the maximum and minimum values is, let us say, 8 mm. So therefore the amplitude will be half of that, therefore 4 mm. So therefore delta y is r square upon square root of 1 minus r square the whole square plus 2 zeta r whole square. Which is equal to, so r here is equal to omega by omega n, which is 50 by 4 is 25 by 2, which is 12.5 radians per second. 12.5. So not radians per second, just 12.5. The value of this expression of z by y is equal to 12.5 square from square root of 1 minus 12.5 whole square plus 2 into zeta into, which is zeta is equal to 0.1 square. To zeta into so the ratio of z by y is ratio of these two quantities, which is so y will be point will be z divided by 1.006311. This will be nearly equal to z itself. So y will be somewhat nearly equal to 4 mm itself. So I guess the correct option to this is option D. So let us look at some other kind of examples from which were left from the earlier week. So these were the examples that I had related to the vibration measurement instruments for this week. So let us look at some other questions. So let us look at this question. So this question appeared in one of the GATE exams. So it has been given that a spring mass damper system. So it has a mass M, stiffness K, and damping coefficient C. It is excited by a force F of T, uh, is basically B sine omega T. And where B, omega, and T are the amplitude, frequency, and time respectively, as it is shown in the figure. So we have been given four different kinds of responses over here, and we have to match these type of responses to the particular conditions, or basically the parameters which for which the response will be observed. So here uh, we can see that for the first parameter set is basically our usual thing, where the damping coefficient C is greater than 0, and the frequency with which we our forcing frequency is equal to root k by m. So it is operating at resonance. So what is happening is, in this case, is that by with the force f of t, when the forcing frequency matches the natural frequency, so then energy will keep on adding to the system, and so it will keep on adding energy to the system, but at the same time damping is also dissipating some energy from the system at the same time. So therefore the response is controlled by because of the damping. So the response given in the first option seems to be the correct one. So it seems that the option P, the parameter set P, the correct response for that is the option 1. Now the second case would be where C is less than 0 and omega is non-zero. So here in this case where we have negative damping, so the forcing frequency force F is also adding energy, and at the same time, so when the damping is coefficient is positive, it dissipates some energy. But now when the damping coefficient is negative, we keep on adding energy into the system. So the forcing F of T is also adding energy into the system, and in addition to that, the damping is also adding some more, keeping adding an energy into the system. So the response which is given in the option number 4, which where the response keeps on increasing at a exponential or polynomial sense uh, with time, that seems to be the correct one for the option C. Now let us look at the third set of parameters, where there is no damping present in the system and the frequency matches the resonant frequency. So here now, because there is no damping present in the system, so the response of the system will keep on growing with time, uh, and so since energy is continuously being added, the amplitude of the oscillations will keep on growing, and so therefore uh, the option number 2 over here seems to be the correct one for this set of parameters. So therefore we will put that the correct response for this parameter set is option number 2. So then we are left with option number 3, uh, the response number 3, which we have to match it. So the parameter set S where C is equal to 0, where there is no damping present, and omega is nearly equal to K by M. So omega is not exactly equal to the natural frequency, but it is close to it. So then we will observe the phenomenon of beats, so where the amplitude will start growing with time, and then after some time it will again start decaying. So this kind of a trend is shown by the response shown in the option number 3. So therefore S seems to be the matching with the response for given in option number 3. So if we now compare these options with the options which are given in the question. So P matches with 1, Q matches with 4, R matches with 2, and S matches with 3. So option C is the correct answer to this question. So let us look at this question. So that a machine of mass 200 kg is supported on two mounts, each of stiffness K is equal to 10 kilonewtons per meter. So the machine is subjected to an external force F of t is 50 cos 5t. So we are assuming that only vertically translatory motion is being done. So let us assume that there are some rollers which constrain the motion of this block along the vertical line. So the magnitude of dynamic force transmitted from each mount to the ground is being asked. So what will be the force that is being transmitted to the ground? So that is because of the spring force. So let us draw the free body diagram for this mass. So F is the frequency, the forcing frequency, and so let us say if x is the displacement of the mass, and let us apply Newton's second law to this block. So we will get F minus 2kx is mx double dot. So mx double dot plus 2kx is equal to F. So let us assume a solution of the form x e to the power j omega t, and F is equal to F naught e to the power j omega t, and let us substitute this into the differential equation. So x double dot will be equal to minus omega square x e to the power j omega t, and F, and so therefore let us substitute this into the differential equation. So we will get minus omega square m plus 2k into x e to the power j omega t is equal to f naught e to the power j omega t. So therefore the steady state amplitude capital X will be given in terms of the steady state amplitude of the force F naught as 2k minus m omega square dynamic force transmitted from each mount to the ground. So it will be basically 2kx will be the force transmitted to the ground. So the force transmitted to the ground, we can write it as 2k f naught upon 2k minus m omega square. So here mass is 5 kg. No, sorry, it's not 5 kg, it's 200 kg, and the stiffness is 10 kilonewtons per meter. And F naught is 50. So the force transmitted to the ground, we can calculate it as 2 into 10,000 into 50 divided by 2 into 10,000 minus 200 into. So omega is 5. So it will be 50 upon 1 minus 200 into 25 by 2 into 10,000. So this will become 100. Two hundred by 3. So like this is the magnitude of the force that is transmitted to the ground. It's about 66.67. So this is how you can solve this problem. So I see one participant has joined. So hi Virendra. Right. So yeah, thanks for joining this session. So uh, so I just see that you just joined few minutes back. So So can you please just unmute yourself and just briefly tell about yourself?
Very good evening, sir.
Hi.
I'm
Yes.
audible?
Yes. Yes. Yeah. Please go ahead.
Okay. So myself, Virendra Matpati, sir.
Yes. Hi. Hi.
Uh,
Yeah. So where are you from?
I'm from Maharashtra, sir.
Okay. Where in Maharashtra?
In Maharashtra, Nanded.
Nanded. So are you a BTech student?
No, no, no. I'm actually lecturer.
Oh, you are a lecturer. Okay.
Yes,
Uh,
yes, sir. Yes,
so
sir.
you are teaching in some college.
Yes, yes, yes. In government college, sir.
Okay. Which college? Uh,
Government polytechnic.
okay. Okay. So what
Yes.
what is your motivation to join this course?
Actually, I have completed my post graduation in machine design and analysis,
Okay.
and my MTech project work was in non-linear vibration.
Okay.
Oh, that's why I have joined this course. Have
Okay.
you- Yes, sir.
Okay. So your MTech project. So are you you have completed your post graduation? You said. So are you pursuing
Yes,
PhD?
yes. Not planned, sir, yet.
Okay.
In 2014, I have completed from NIT Rourkela.
Okay.
Yes,
So
sir.
okay. Okay. You have completed your post graduation from where? You said NIT.
NIT, National Institute Rourkela.
Okay, Rourkela. Okay, great. Yeah,
Hmm.
thanks. Thanks for joining. So, what brings you to this course, sir?
Just now I told you, sir, my project work was also in vibration only.
Yes, yes. But
So I'm planning to complete my PhD now.
okay, okay,
That's
great.
why I have joined this coursework.
Okay, great. So this course is actually, so since you have already done some work on vibrations, so this course is like a basic introductory course. So
Yes, yes, yes,
so
yes. But
hopefully, yeah,
actually, if I'm going to apply in some NITs or IITs, definitely they will ask for coursework, isn't it?
right,
So I just want to show them that yes, I have also covered this basic knowledge. Once
right.
if I will show them that this passing certificate,
Okay, okay.
definitely they will understand that okay, he has some knowledge, basic knowledge.
Sure, sure, sure,
That's
sir.
why.
Yeah, yeah, sure.
Yes, yes, sir.
Yeah, yeah.
Yes,
Hopefully, this course will be helpful for you. So my
yes,
name
surely,
is
surely, sir.
yeah, yeah. So my name is Parth Joshi. So I am actually pursuing PhD at IIT Bombay, and
Okay, okay, sir.
yeah. So so I am actually
Okay, you are Miss
conducting yeah.
TA.
So I am actually conducting these tutorial sessions every week.
Yeah, okay.
So
Okay,
I
okay.
think are you attending or trying to watch at least the recording of these sessions?
Yes, 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 sir. Yes, yes. YouTube. Actually, you are uploading on YouTube also, na?
Yeah, yeah, right.
Yes, 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 sir. Yes, sir. Also
Yeah,
in
yeah,
NPTEL SWAYAM tab, there is problem solving session.
exactly.
So
Yeah,
there are PDF and videos both.
right, exactly. So yeah, please do go to the earlier week's videos and those whatever lecture notes. So and
Sure. Okay,
yeah.
okay, sir.
So and if you have any questions or anything, you can always post in the discussion forum for that course to get. So if you have any questions, please do let me know. So
No, till now I don't have any questions, sir. I just
yeah,
actually
yeah,
only few second back I have seen that link. I was
yeah,
just
yeah.
checking my mails, then I got that link about the problem solving session. Sir, is
Ye-
the time fixed about problem solving session?
Yeah,
Means
so
on Monday,
yes, yes. So this session will be
every week Monday?
yeah, so this session will be every Monday 7 to 9 in the evening. So
Okay, okay, sure, sir.
so if you are
Now I think this fifth week is going on now.
yeah, this is the
Problem solving also for sixth week.
fifth
Fifth.
week. Yeah, this
Okay.
is the fifth week. So there are still
Just 3 weeks.
3 weeks more to go. Already 4
Okay, okay,
weeks
sir.
completed. So this session's
Yes.
recording will also be made available. So if you are available, so please do attend in the next subsequent whatever weeks
Huh.
that are left.
In next week,
And
I will definitely attend, sir.
yeah, okay, sure.
Okay. Oh, thank you, sir.
Sure, sure. Thanks for joining. Please do attend
Yes.
the next problem solving session. So if you have any particular problems, please do let
Okay.
me know. I'll try to answer them in the next
What I
weeks.
will do, sir, in next week, I will ask, sir. Hmm?
Sure, sure, sure.
I will figure out first, hmm?
Yeah, sure,
And
sure.
then I will ask, sir. Hmm?
Yeah, sure, sure. Thank you.
Okay.
Yeah,
Okay.
thanks for
Thank
joining.
you so much, sir.
Yeah, thanks for
Thank you, thank you.
joining. So we'll
Okay,
close the session for today, and
okay, sir.
we will meet in the next week.
Okay, thank you, sir.
So thank you. Yeah, thanks for joining.